Hi guys, welcome back. This is Algebra 2. We're doing Lesson 3 practice. It's numbers 1 through 4 on page 9. Here we are identifying the scenario as either linear or exponential, and then we're writing the equation and using it to make a prediction. All right, this is where I've enjoyed teaching this because it does involve real-world scenarios. So in this case, number 1, cell phone ownership among teens is growing by 25% each year. Currently, about 30 million teens own a phone. All right, so we are going to write an equation to model this situation. We're going to predict how many teens will have cell phones in 2 years. And first we have to decide if it's linear, a basic exponential equation, which it doesn't have a percent or a decimal in the growth rate. It's like doubles or triples. And then percent exponents. Obviously, this is a percentage exponential equation because we do have 25%. All right, so we're going to write our equation. So I'm going to write it to the side here because I have some more room. So y equals, now what's my starting value? My starting point right here is 30 million. So that's currently, we're starting here at 30 million. So that's a lot of zeros. So I'm going to write that. Now I do my growth rate. If it's growing by 25% each year, so this goes back to our 1 plus a percentage and 1 minus a percentage. This is going to be a 1 plus because we are growing. Now, 25% as a decimal, we move 2 places over to the left. So it's 1 plus 0.25. And that's going to be our growth rate. So we add 1 and 0.25 together. So we're going to do 1.25. Once we have our growth rate, we put our little x for the exponent. And then boom, we have our equation right here. Now, to figure out how many teens will have cell phones in 2 years, that 2 is now my x value. That's my input. So I'm going to put 2 into the exponent and then multiply it by 30 million. All right, so I don't even know if my small calculator can do this. It's going to be 1.25 squared, because you're going to put 2 in for the x, so that's 1.25 times itself. And I'm going to multiply that by 30 million. And look at that. Here's how many teens are going to have a phone after 2 years. That is going to be 46,875,000 teenagers with phones. That's how we do number 1. All right, number 2. A tennis tournament starts with 192 players. Each round, the number of players is halved. All right, so we're going to write an equation to model the situation, but first we have to decide, is it linear, basic exponential function, percent exponential function? This one is definitely basic, all right, because my growth rate is basically either a whole number or a fraction. There's no percent, there's no decimal. All right, so halved just means it's being divided by 2. So 1 over 2 is going to be my growth rate. All right, so here's my equation. Y equals, well, I start with 192 players, right? And then after each round, the players are halved. So I'm going to put a fraction, my 1 over 2, and I'm going to put my little x for my exponent, and there is my equation. Y equals 192, 1/2, and then x. Now, just like we did before, that 3 is my input, my x value, so I'm going to plug 3 into my x, and then that's basically going to mean 1/2 times itself 3 times. All right, so I'm going to do 1 over 2, 1/2. I'll divide, or I'll convert that to a decimal, which is fine. 1/2 is a decimal is 0.5. I'm going to multiply that by itself 3 times, because 3 is my exponent. So 0.5 times 0.5 times 0.5, that gives me 0.125. Now, that's not my final answer, because now, order of operations, I have to multiply that 0.125 by 192. And then that will tell me how many players are still left after 3 rounds. So that 0.125 times 192, that gives me 24. So 24 players will be there after 3 rounds. Okay, 2 more. The population of rats in your area is decreasing at a rate of 3.5% per year. Good thing they're decreasing. You have counted 80 rats so far. So we're writing an equation to model the situation. Do I have a linear, basic exponential, or percent exponential? Well, because we do have a percent right here, it is a percent exponential. All right, so here's my equation. I'm going to put it over to the side again here. I have y equals, so you've started the count at 80. So that's going to be my starting value. So 80. If it's decreasing at a rate of 3.5% per year, how do I figure out my growth rate? Well, that goes back to the 1 minus my percentage. So it's 1 minus, now what's 3.5% as a decimal? So I'm going to move that 2 places over to the left. So it's going to be 1 minus 0.035. And that's going to be my growth rate. So I'm just going to plug that into a calculator real quick. 1 minus 0.035, make sure it's 0.035. That is 0.965. So there is my equation. Well, now, what's the population of rats after 5 years? So same thing that we've been dealing with before. That 5 is going to be my x value. That's what I'm plugging into the exponent. So it's 0.965 multiplied by itself 5 times. That's how exponents work. All right, so 0.965. And there's a handy little exponent button on this calculator. All calculators are different. So I'm going to do 0.965. My exponent button here is that xy. So I'm going to press that. If you're using a different calculator, you can confirm what you get. I'm going to put in 5 because that's my exponent. I get this big, huge, long decimal. Now that's not my final answer because order of operations, I now have to multiply it by the 80. So that number times 80. So that's going to be 66.946. So after 5 years, I have 66.946 rats. Now obviously, in real life context, you can't have 0.946 of a rat unless a cat eats its head off. So you can round that up to 67. Very last one. On Monday morning, there were 4 inches of snow on the ground. Not enough for a Delaware City School snow day, unfortunately. Each hour, 0.5 inches is added. Well, maybe the next day then. All right. On Monday morning, there were 4 inches of snow. Each hour, 0.5 inches added. So that is a constant. We're not multiplying anything. We're not dividing anything. So it is going to be a constant, and that's linear. Anytime we have each hour, like the word per, that means slope. So 0.5 inches, per what's going on per hour, I'm sorry. So it's going to be linear. So we have a slope-intercept form, y equals mx plus b. Okay, so y equals, my slope is 0.5. Now, since it's being added, that means I have a positive slope. So it's going to be 0.5x, and then don't forget your y-intercept, which is the initial amount, 4. Okay, so we want to figure out how much snow is on the ground after 2.5 hours. 2.5 is my x value. All right, so I just plug in 2.5 into that x of my equation that I made, and I just do those calculations, and I figure out how much snow is on the ground after 2.5 hours with the initial 4 inches of snow already there. So I'm going to do 2.5 times 0.5, which is my slope, multiply that by 4. You have 5 inches of snow on the ground, 5 inches, after 2.5 hours. Maybe a potential snow day. We'll see. All right, thank you so much.